it out loud just so that I remember to do it, if nothing else. Okay. I want to share my screen. All right, so in this challenge problem we have, we're asked to calculate the density of a substance as well as its length of the side, given some information about the crystal lattice. So here in the OneNote or in the class notebook, you will see I've added some additional resources that are there, some of which are in the lecture, but some of them are not. So we can see when we talk about these crystal lattices, right, it's the smallest repeating unit inside of this crystal structure, right? So if we break that repeating unit down to the smallest size, we get these crystal lattices, and there's a whole bunch of them, right? And if you're a marine scientist and you take geology, you probably experience understanding a lot of these, right? Because this is general chemistry and it's the very beginning, we are going to be not worrying about all of the different crystal structures. We are simply looking at a small subset, this cubic subset, right? And it comes from the way these molecules or atoms stack together, and we have different crystal stackings that are going to lead to these, right? And these are all cubic close packed structures, which means that we can have these three simple cubic structures. Right? I'm going to change my color from rainbow back to red. Right? And we can define these. We can talk about the simple cubic is where we just have atoms at the corners, right? And here these dots, I think of it just representing the nuclei, right? If we talk about the electron clouds, that's where this sphere comes in, right? And the nuclei are going to be centered at the corners. So we can see that each one of these circles in this middle one is going to be subsected or dissected or transected or whatever the right sected term is, by a whole bunch of different squares, right? So each one of these circles here in the simple cubic represents or is split between 1/8 or 8 different cubes. So 1/8 of this atom is in there. So if there are 8 sides, we're going to have the equivalent of 1 atom's worth of material in this. Right? If we look at how this crystal is oriented, right, then we can talk about this length of the side here is essentially 2 radius. So the length of the side, which we're going to call A, is equal to 2 times the radius, right? Because it's essentially from this distance to the center and from this distance to the center. Or we can break this apart and each one of those is R. Or here, each one of those is R. Does that make sense? So the length of the side, which we're going to call A just because I don't have a good reason for it besides the book does, we're going to call it 2R. And when we talk about this density or the amount of material in the cube, we always talk about, especially density, is mass divided by volume. So the volume of the cube is going to be not 3A. A cubed, right? The length times the width times the height. Since it's a cube, they're all going to be the same, right? So, does that make sense? So whenever we talk about determining anything about these cubes, we're always looking for the volume in the cube, which is going to be 3 times that edge length. And the work really for this is to determine what that edge length is. For the simple cubic, it's fairly straightforward because those are actually touching. When we do some of these others, we don't see that. And inside the cube, we have the equivalent of 1 atom's worth of material. And another thing that we can talk about in terms of these crystals is how what we call coordination number. If we look at this single atom here, how many atoms is that one touching, essentially? How many nearest neighbors does it have? Well, if we look here, it is touching this one, it is touching that one, it is touching this one, it is touching one above, and it's touching one out here, right? And then there's one out on this side, which I don't know how to draw, out there, right? So it's out in front of that. So this has what we've referred to as a coordination number of 6. It has 6 nearest neighbors that it is sort of that are surrounding it. Right? Okay, so that's the simple cubic. If we look at the face-centered, now in addition to atoms at the corners, we stick an atom on the face of each one of these cubes. Right? So again, we can see it here. Now, if we look at this distance A, it is no longer dependent on those 2 corner are not touching anymore, right? We can see that a little bit better here, right? There's some distance between there. So we have to then use geometry to draw this right triangle, right? And this, the hypotenuse of our triangle, goes through now 4A. So because of the beauty of math, our A is going to be equal to the square root of 8R. Right? Or you will also see that if we reduce it as 2 square root of 2R. Either one of those is appropriate. The geometry or the algebra to do that, to get that number, isn't that hard to do if you want to do it, but I'm just going to say that that's the result, right? The length of this side is the square root of 8R. So we're going to take the radius of the atom, multiply it by the square root of 8. Right? Now, that's A. If we go back to the number of atoms within this box, we still have 8 atoms at the corner that have 1/8 of the material in there. But now we have these 6 faces. Right? And if we look at this one, we can see that that is cut in half. So we have 6 faces where half of the atom is inside the box. So we now have a total of 4 atoms worth of material inside the box. And if we look at the coordination number, again, if we count the nearest neighbors to this one, we have 1, 2, 3 inside the box, and then there's going to be 3 inside the next box. So this has a total coordination number of 12. Okay. And our last one that we want you to be worried about is this bodied centered, where we have, again, atoms at the corners, but now we have an atom completely inside, right? So we can see this. The length of the side here, A, again, now our triangle doesn't go through, we can talk about this side, but now it actually goes from this corner through to this corner and then back, right? So our geometry just got, it's still the Pythagorean theorem, but our triangle looks a little different. And when we solve that, we end up with 4 times r over the square root of 3. Again, if you want to go through that math, we can, but it's Thursday, so we're just going to trust me when I say that the length of the side is 4r over the square root of 3. Right? If we go to see how many atoms are inside this box, we still have 8 at the corners, total of 1. Now we have this 1 completely inside. So this has a total of 2 atoms worth of material inside the box. And our coordination number, this was the easiest to see. If we look at how many atoms that center atom is touching, we see that there are 4 on top of it, 4 on bottom, so it has a coordination number of 8. All right. So that's just general information about these 3 simple cubic lattice structures that we're going to need to answer problems. Okay. So that's sort of a review of what the solid structures. Let's come back up here to the problem. So we have lead, and then it's saying it's adopting a face-centered cubic crystal structure, right? So we are using this structure for our lead. If it has a length of this unit cell, the edge length A, as 495, we want to calculate the atomic radius and also the density of lead. Right? So we now have lead that is a face-centered cubic structure where our edge length A was 400, and I can't remember numbers for 4 seconds, 495 picometers. So we want to calculate R and D. So we're going to do R first. If we look up here, R A is related to R. So for a face-centered cubic, A is equal to the square root of 8R, right? So that means that R has got to be equal to A over the square root of 8, which is equal to, miracle of math, 175 picometers. And typically you're given this value and you actually have to go back to this one, but today I wanted to be a little nice to you, so we're going the other one. So the radius of the leads in this crystal structure are 175 picometers. Okay. So now the more fun one. Calculate the density. Density is mass divided by volume, right? So we have to figure out the mass that's inside the volume, or the cube, and then the volume of the actual cube. Right? So we're going to do these sort of simultaneously. So let's talk about the volume first. So when we solve for density, typically we use grams per centimeter cubed, which is equivalent to grams per milliliter. So we typically talk about density in grams per milliliter, but that's the same as grams per centimeters cubed. So we have to convert our length of our side into centimeters, right? So to find the volume of the cube, we take the length of that side and cube it, correct? And the length of our side is 495 picometers, but we need that in centimeters. So then we have to convert between picometers and centimeters. Right? And because I don't want to memorize the conversion, I'm going to do conversion to meters. So 1 picometer is 1 times 10 to the negative 12th meters. And then we're going to go to centimeters. 1 centimeter is 1 times 10 to the negative 3 meters. So that's going to give us our length of that side in centimeters. And then we cube it to get the volume. Everybody okay with that? Any questions about that part? All right. So now, if we come back up to, we have to calculate the mass that's inside of this cube, which is going to be essentially equivalent to the number of atoms we place inside that cube, right? So for a face-centered cubic, we have the equivalent of 4 atoms worth of material in that cube. So for our mass, it's going to be the mass of 4 atoms of lead, right? But we need to convert to grams, so we get to do a whole bunch of fun dimensional analysis, right? So when we talk about mass, in grams, we have to go through moles. So the first thing we get to do is convert from atoms to moles. And we know that there are 6.022 times 10 to the 23rd atoms. Ooh. In 1 mole of lead. And for every 1 mole of lead, it has a mass of 205. Oh, and by 205, I mean 207.2 grams. Everybody follow me with that? So let's just take a second and think about this. Is this box really big or really small?
Really small.
It's really small, right? So we would expect the volume, this number, to be this number, I always forget you can't see me use my finger, to be really small, right? And correspondingly, the amount of mass inside of that box is going to be small, right? So when we do this math, we should expect a small number over a small number. And when we do that, I get 1.332 times 10 to the negative 21 grams and 1.213 times 10 to the negative 22 cubic centimeters. Because we're talking about a really small box that contains a really small amount of mass. And when we do that, we take 1.332 times 10 to the negative 21 divided by 1.21 times 10 to the 22nd. We end up with a density of 10.98 grams per centimeter cubed. Questions on that? All right. So the things that we can do now is if we know the density and we know the type of crystal it has, we can figure out the molar mass, for example, because we can figure out how many atoms or the number of moles of something that's in that box, right? And we know the number of atoms, so we would be able to calculate the number of the mass inside that box. So we could calculate, if we know the density and the type of packing, the molar mass. Or if we know that the atom, the type of packing, and its radius, we could calculate density. Or if we know the density and the type of packing and the element, we could calculate its radius. All of these are going to go through a very similar process where we're going to use the amount of atoms contained in the box and the size of the box to interrelate all of those different issues. Okay? And typically we are going to be working in grams per centimeter cubed or grams per milliliter. They're essentially the same. Okay. Questions on that? Questions on anything? AJ, did that answer your question?
It did, thank you.
All right. Others? All righty then. Let's get into our groups and start working on today's activity.